Okay, so question 1 is a big catch-all question about hydrocarbons, so you need to have done quite a big chunk of organic chemistry revision before you can really get stuck properly into this one. First 3 parts are all sort of short 1-mark questions, so for this particular paper you could get away with quite short answers, but in each case remember that you probably need to be able to say a bit more on another occasion. So first of all, why can you separate why can you separate crude oil into different fractions? All that's getting at is the idea that different hydrocarbons have different boiling points, and that's the basis of separation. That would be your 1 mark. But more generally, you need to be able to expand on that, so the method that separates them based on boiling points is called fractional distillation, and you should think of that whenever you're asked how would you purify this organic liquid from whatever. So it might be, for example, if you make ethanol by fermenting sugars in aqueous solution, you use fractional distillation to purify the ethanol out from that mixture. So think of that as a general way of purifying organic liquids. And of course you need to be able to explain why different hydrocarbons, for example, have different boiling points. So you need to be ready to talk about van der Waals forces and how they're affected by the contact surface area and the number of electrons in the molecule and so on. So lots of things they could have asked you, but in this case all they wanted was different boiling points. Okay, part B, why should we use more biofuels? The key thing here is that this is a comparison. It's saying why use these rather than petrol or diesel, and that means your answer has got to say this is what's good about the biofuels, whereas this is what's less good about the petrol and diesel. If you don't do it as a comparison, you'll get no marks. So there are 2 possible issues really to base your answer on. One is the renewability thing. So biofuels are renewable because you can always grow more crops to make more of them, whereas fossil fuels are not renewable because they take many millions of years to form. That would be a good answer for going down that route. Or you can go down the carbon dioxide climate change route, so you can say that when fossil fuels are burnt, new carbon dioxide is added to the atmosphere, which will increase its concentration and therefore leads to global warming, whereas when you burn biofuels, you don't add new carbon dioxide because when the plants grew, they took in carbon dioxide, you turn the plants into fuels, you burn them, and the carbon dioxide goes back into the air, but new carbon dioxide isn't added. So that's better because it doesn't, therefore, contribute to increasing the CO2 concentration, and therefore doesn't contribute to climate change. Either of those would be fine. You didn't need to spell them out in huge detail for your 1 mark, obviously, but be ready if it was 2 or 3 marks, that's what you should be talking about. Okay, this is C12H26 dodecane, and it's saying to you, if you crack it, why can you make a variety of different alkanes? So all it wants is the idea that the chain can break at different points. So for instance, it might break there and give you, say, that alkene and that alkane, or equally, it might have broken somewhere else entirely, like there, and given you that alkene and that alkane. But remember, it's always, every time it breaks, you get an alkene being formed. There can only be 1 alkane product, otherwise the hydrogens won't balance out. So it could also break more than once. So it might break there as well, and you might get that and that and that. Okay, so lots of possibilities. So all you have to say for that question was because the chain can break in different places and it can break more than once. Okay, now part 2 of that question is exploring that issue a bit more precisely, and it's important that you read this kind of question carefully. It's 4 marks, it's giving you quite a lot of information, so don't rush into it. Make sure you know what the information is that's there before you get stuck into it. So the first thing is that we've got this alkene A, so we know that A is an alkene because it tells us that, and that's important, that you don't sort of go wrong and start thinking about other possible structures that might fit the data. And in the mass spectrum, it gives peaks at 15, 27 and 42. So remember, a mass spectrum looks like this. m over z along the bottom, which is mass divided by charge, but for our purposes you can just think of that as mass, okay, because the charge is effectively +1 always for these fragments, is what we're thinking. So we've got a peak at 15 and 27 and 42, and it tells us that 42 is the one with the biggest m over z value, and that peak, remember, is called the molecular ion peak. Okay, and what you interpret that as meaning is that the entire molecule, just having lost one electron so that it can form a positive ion, but the entire molecule with all its original atoms is still there, and that's what we call the molecular ion peak. And the importance of that is that for that peak only, m over z is equal to the MR of the compound. Okay, so a molecular ion peak is very useful because it gives you the MR, in this case, of alkene A. And that's really the place to start, because 42 is quite a small number. There can't be very many candidates for an alkene with an MR of 42. So good way to start is to think, well, how many carbons is that going to be? So you can see 4 carbons, too many, because 4 12s are 48, so that's not possible. 3 12s, 36, that looks possible. So C3, 36 leaves 6 left over, so C3H6 looks good, because that's CnH2n, that fits an alkene. C2 is not possible, because that would be only 24, and that would leave it needing a huge number of hydrogens, which it couldn't do. So that is the molecular formula of alkene A. And of course, because it's only got 3 carbons, there's only one candidate, which is propene, which is that. Okay, so that's what alkene A is. Okay, we've got to identify the particle responsible for the peak at m over z is equal to 27. So if this is alkene A, a fragment happens by breaking one bond in the molecule to release a smaller positive ion. So remember, in the mass spectrometer, your propene will have become a positive ion. So if we write it out a bit more fully, it's going to be that is the molecular ion that's going to fly through the mass spectrometer. And fragment peaks arise when that molecular ion falls to bits. And for our purposes, we only consider the possibility of one bond breaking when it fragments. So in this case, you can see there's only really one option. I mean, obviously hydrogens could break off, but that's not very interesting. In terms of generating fragments with significantly different sizes, we're not going to be able to break the double bond, because that's 2 bonds to break in one go. So that has to be what happens. That bond breaks. And you can see that if that happens, there are 2 possible fragments you could get. You could either get CH3+, or you could get CH2+, which is probably easiest to write it like that. Okay, so those are the 2 possible fragments, and one of those hopefully should have a mass of 27, and indeed if you add this one up, 2 12s 24 plus 3 hydrogens makes 27. So that is the answer. That's the fragment that gives the peak at 27. And then we've got to write an equation for the cracking of C12H26 to make the alkene. So this is one of those occasions when I think it's fine to use molecular formula. Generally, you need to be very wary of molecular formulae in organic chemistry because they tend to be ambiguous, and so you can be accused of not giving enough information. So try and avoid writing them, whether it's in equations or just generally when you're talking about things. You should usually try and write the carbons out explicitly. But here, I think because we've already established what the structure is, and because they've used C12H26 in the question, it would be fine to stick with the molecular formulae. So what we know is that it produces propane, because it tells you that in the question. I think, is that right? Yes, it does tell you that in the question. So that's C3H8, and then several molecules, it says, of alkene A, which we now know is C3H6, and obviously to balance it up you can see that that has to be 3. Just check the hydrogens balance. 3 6s are 18 plus 8 makes 26, so that looks good. And that's the way a cracking equation should always look. that you may get two or you may get more than two products, but only one molecule can be an alkane, then there may be one or more alkenes produced as well. So that's your equation. You could, if you wanted, write it out with skeletal formulae, so you could get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Will give you propane plus 3 propene, and that would be fine. Or you can write it out with other ones, but obviously it becomes increasingly long-winded, and you're not really going to want to do anything more than that. Okay, so the second part of that question is mechanisms, and it's really, really important that you grit your teeth and get stuck in and learn the mechanisms that you need to know for this exam in detail. And the way to do that is not to just try and memorize them as kind of random sets of squiggles and things that you've somehow got to reproduce, but understand them. Because once you understand them, you know, that's what organic chemistry is all about. That's what makes it interesting and real science. So it will help you with everything if the mechanism makes sense to you. Okay, so this one is particularly easy because often they take a mechanism that you've learnt and ask you to modify it slightly. You know, so you've learnt it for ethene reacting with bromine, but they might ask you for a different alkene, a different halogen, and you've just got to be careful to adapt it. But it's, you know, it's very easy, you've just got to be careful doing it. But this one actually is the one you've learnt, so this, no excuses for not getting full marks on this really, because you've just got to learn it straight from the notes. Okay, so it asks you to name and describe the mechanism. So we'll come back to the name at the end, because once you understand the mechanism, the name makes more sense. Okay, so here is ethene again, and it's reacting with bromine. So I'll write on the board basically what you need to have in your answer, but we'll talk about it in a bit more detail than that to make sure that you know, you're really getting to grips with all of this and that it makes sense to you. So remember, the story is, as the bromine comes in close here, what it notices most about this alkene molecule is the pi bond. Because remember, those pi bonding electrons are kind of marginalized a bit, they're squeezed out to the sides, away from the plane of the alkene, because they're formed from those sideways overlapping p orbitals. And that means that they're very much in the face of this bromine as it comes in here. And because electrons hate other electrons, you know, negative charge repels negative charge, the effect of seeing this big cloud of pi electrons here is that the electrons in the bond between the two bromines are going to be repelled by that. Okay, negative pi electrons here repel negative electrons in that bond, and they move towards the back, and that creates a dipole. So this bromine suddenly has a dipole that obviously it wouldn't normally have. It's an induced dipole resulting from repulsion from the pi bond. And the closer it gets, the bigger that dipole gets. So that eventually it gets so big that the pi bonding electrons think, right, we're kind of fed up of being pi bonding electrons. It's not a great thing for electrons to be, because, you know, in a pi bond you're not in the best place, you're not tucked right down closest to the two nuclei, you're squeezed out to the sides or you're a little bit further away from the nuclei. That's not great. So that when they see this bromine, which remember is a very attractive nucleus, group 7 elements, very good at attracting electrons, so they see that bromine and they think, let's go for it. This is our chance to form a sigma bond, and a good sigma bond at that. And so that's what happens, and that's where your curly arrow comes in. Okay, a curly arrow represents movement of a pair of electrons. They sometimes ask you that, so you have to be ready to explain. Curly arrow means movement of a pair of electrons, and specifically it's the pair of electrons which form that pi bond are going to move out of that bond and be grabbed by that bromine. So you have to draw the arrow very precisely from the bond to the bromine to show that. At the same time, this pair of electrons that's forming this bond here, that's the last straw as far as they were concerned. They were already being repelled by this electron pair when it was there. Now that it's come right in here, they're going to say, right, we're off out of here, we don't want any more to do with this. And so they leave this bond and they move all the way out onto that bromine. And again, that's what your curly arrow needs to show. So it needs to come from the bond and show that pair of electrons moving out and now becoming a lone pair of electrons on that bromine. So that's what happens in the first step, and that gives you your intermediate, which will look like this. Okay, so all the atoms in the alkene are already there. But what's changed is that's no longer a double bond, because that pair of electrons has been grabbed by the bromine. So now we have a new bond to bromine here. This carbon has lost out, because it used to have a half share of that double bond, but both of those electrons are now here, so this one is down by one electron, and it therefore has a positive charge. Okay, and it's very important. It's not just delta positive, it's a full positive charge on that carbon. So this intermediate is called a carbocation, and that means that it's got a carbon with a positive charge on it. That type of bond breaking process, remember, where both of the electrons from the bond are used by one of the carbons, in this case to form a new bond, the other one gets none of them. That's called heterolytic fission. You didn't need heterolytic fission here, you didn't need carbocation. Those words weren't asked for, but often they are, so make sure you know what they mean. Meanwhile, this bromine has now become a bromide ion, because it used to have a half share of this electron pair, but it's now got both of them, so it's up by one electron, so it's Br minus. Not just delta minus, but Br with a full negative charge, and it has a new lone pair that it didn't used to have. Okay, it's got three other lone pairs as well, but we don't bother showing those because they were there already. What we show is this one because it's new, and it was formed from breaking that bond and using that electron pair to form the new lone pair. So that's our intermediate, and now we're almost there, because the last step is sort of obvious, that this negative ion is going to be attracted to that positive one, and they can come together to form a new bond like that. Again, the curly arrow's got to be very precise, from the lone pair to the carbon with the positive charge. Okay, but it's got to be from the lone pair, and it's got to be to the carbon atom, otherwise they're not going to give you the mark. And that gives you your product. So we've got all the existing atoms that were in the ethene to start with, and now we've got two bromines attached down here, and that's it. It's all finished. As I said, in these mechanism questions, you've got to be very careful that you read and see how much information they need, because that's the sort of drawing part of it, but they may want lots of words as well. In this case, the only words they wanted, in fact, were the name of the mechanism, and it's called electrophilic addition. Okay, so that was the other bit you needed to complete your marks. Just remind you why it's called that. Addition, fairly obviously, because the organic molecule didn't lose any of its existing atoms. It simply added more on, so that's why it's called addition. Electrophilic comes from the fact that what the bromine is doing here is accepting a pair of electrons. That's what that curly arrow shows. It's accepting electrons coming in from there, and an electron pair acceptor is called an electrophile. That's one of the definitions that you should be learning. Okay, so electrophilic addition. Right then.